Okay, well, welcome everyone back. So, hope after a 1 hour break, everyone has been fully recharged. So, this afternoon's talk given by Professor Pontus Gieselsson from Rende University. Pontus currently is an associate professor in Rende University. He got his PhD from Rende University in 2012. So from 2013 to 2014, he was a postdoc with Stephen Boyd in Stanford University. Pontus' research interests include mathematical optimization and its wide range of applications in automatic control, machine learning, signal processing, and wireless communication. Pontus has already received several prestigious author prize. So for example, he received the Young Author Prize at the Advanced Control of Chemical Process FX Symposium in 2012, the Young Author Prize at the FX World Congress in 2014, and the Ingvar Carlsson Award from the Swedish Foundation for Strategic Research in 2015. So thanks again, Pontus, for coming. So now give the stage to you.
All right, thank you. Thank you for inviting me here to give this talk and also for the introduction. So my talk today will be on a similar topic as Pontus's talk, but still quite different. We will stick to convex optimization in this talk, but the algorithms we will be talking about are kind of the same algorithms as in Pontus's talk, but what we will essentially talk about here is a unification of these methods. So you saw at least proximal gradient method, and you saw Bregemann versions of proximal gradient method that we will briefly touch upon here. You also saw ADMM and Douglas-Rachford splitting. And these methods seem quite different when you just look at the update equations. But we will, and there have been quite a lot of unifying works that unify these types of methods. For instance, Pontus show this Feger monotonicity requirement that we showed on one slide that you can use to show convergence for Douglas-Rachford in convex settings. The same property holds also for proximal gradient method, for instance. But in this work, we'll introduce a new concept, which is called a nonlinear resolvent that gives rise to a nonlinear forward-backward mapping. And based on this algorithmic construct, we will devise two different algorithms that has essentially all these operator splitting methods that we know as special cases. So the outline of today is roughly as follows. I will start with a preview of what to expect in high-level terms of this talk. And then I will set the stage roughly in terms of talking about some background material that we need for to understand the later parts of this talk. So essentially, I need to introduce something called monotone operators. I don't know how many of you that are familiar with that. Maybe we can have a, probably you can raise your hands in Zoom. So is that possible for you? So if possible, yes. So if you know about monotone operators, please raise your hand, and then I'll see roughly the number of people that have seen that concept before. All right, so I have two or three at the moment. All right, that's good to know. Then I know how careful I need to go there. So after that, we will talk about, you can solve using monotone operators. You can pose an a problem which is called the monotone inclusion problem. So we'll talk about that, different formulations and different additional properties of these problems. And after this, we will talk about algorithms and their primitives. And so this is mostly existing algorithms and the primitives that they use. With that, I mean proximal operators and gradients, essentially. And after we have done this background, I plan to have a short break somewhere here before we go on some new stuff. So this is essentially known things that you can read in some advanced books on optimization. For instance, Rockefeller's convex optimization book, or there is a book by Bauschke and Combet that takes this into very high mathematical detail, and also other sources. And you can see parts of it also in Stephen Boyd's book. All right, and then the second part will be on this new construct, nonlinear resolvent, that I talked about. We will define the nonlinear forward-backward step as an extension of the nonlinear resolvent. And then we will devise some algorithms that are based on the nonlinear resolvent and show how essentially to arrive at other algorithms from our more general algorithm. All right. And please don't hesitate to interrupt at any time if there is something that is not clear, something you would like to have explained more, or just any questions. So please feel free to interrupt. All right. So this is the dense one-slide preview. So many deterministic algorithms. I'm only talking about deterministic algorithms in this talk. So stochastic methods such as stochastic gradient descent and randomized coordinate gradient descent are not included. But many deterministic algorithms for large-scale optimization, such as a projected or proximal gradient method that we saw in the previous lecture. The generalization of that is forward-backward splitting. You saw the forward-backward envelope that was presented in the previous lecture, which got its name from the more general forward-backward splitting method. And then Douglas-Rachford splitting in ADMM. Then there exists a few primal dual methods, which solves both a primal optimization problem and its dual optimization problem at the same time. And two first-order methods that do this are Chambol-Poc and Condat-Wu. Then we have another set of algorithms that is called forward-backward forward splitting and forward-backward half-forward splitting, not as well known. And also the extra gradient method, which might be a bit more well known, that use two evaluations of the operator or the gradient in each iteration. And these can be used to solve, for instance, convex concave saddle point problems and things like that, and have been applied, stochastic variations of these have been applied to train generative adversarial networks, GANs. There is another method called projective splitting. We will talk about the synchronous version of that. There exist asynchronous and block iterative versions that essentially can be used to distribute computations in many computers without, with a different kind of synchronization than in most other algorithms. And we'll also we'll see the asymmetric forward-backward adjoint splitting algorithm, which is a method by Pontus, who gave the previous talk, which includes many of the above algorithms, a special case, actually. And we will also talk about optimistic gradient descent, which has also been used for GAN training, and also a method that we call Malitsky-Tam. And finally, on top of this, most of the methods that we have here, we can do Polyak momentum variation of some of the above. This means that we have the iterate, and then we take some coefficient times the difference of the two previous iterates, add that to our update equation, and this is called Polyak momentum. So we have a very simple trick after we have derived our method to arrive at Polyak momentum variations of most of these methods. So what we will do is to present the unification in a convex setting. And this unification is based on the mathematical project that we have introduced, that is called the nonlinear resolvent. And this is then a mapping in optimization problem space, meaning that we take the x, the optimization variable, plug it into the mapping, and we get another point in the same space back. And what is interesting with this one, or important, that will give us at least one of the algorithms, is that it defines a separating hyperplane between, if we have a point and a solution set of the problem we want to solve. We know that when we apply this nonlinear resolvent, we can define a separating hyperplane that separates the point from the solution set. The problem is that if we just take this algorithm, so for instance, you saw forward-backward splitting as one algorithm. If we take forward-backward splitting, we iterate it, I think it will converge, given that we select the step sizes appropriately. But if we just iterate our nonlinear resolvent, it may not converge. We will see examples of that. So we need some type of correction in order to have a convergent method. So we will present two different corrected algorithms. So one uses a projection correction that projects onto the separating hyperplane, which has some disadvantages, and the other one uses a specific momentum correction to guarantee convergence. And then we see that these two methods have all of the above methods as special cases. So more than developing a specific new method for best possible performance, this is a unifying framework that tries to connect existing algorithms that appear quite different, and it may be very difficult to see the connection between these. All right. Okay, so now it's time to get into the monotone operators framework. So we start out with a gradient property, that the gradient is called is monotone. It satisfies monotonicity property. So if we let f be a differentiable convex function, then the gradient of f is monotone. This can be found, for instance, in Stephen Boyd's book. And what monotonicity means is that we take any points x and y in Rn. We take the difference between the gradients of f at these points. And then we take that scalar product with the points themselves. And this should be greater than or equal to 0. So we can read this thing as the angle between this vector, gradient f at x minus gradient f at y, and the difference x minus y should be at most 90 degrees. So if we look at it in 2D, we have this figure. So if x minus y is this point and 0 is here, then the point, which is grad f of x minus grad f of y, is somewhere in this gray area. The only thing we know is that the scalar product between these two should be positive. And the only way it is not possible if it would be pointing the other direction. So the only thing that it is excluded if the angle between them is greater than 90 degrees. So we depict these monotone operators, this property in 2 dimensions as being in this gray area, given that x minus y is here. And this also has a correspondence in 1 dimensions. So in the 1-dimensional setting, here we plot only x versus the gradient f at x. So it's not a difference anymore. And what we see here is that this is a monotone operator. The slope is 0, and here we have some positive slope, and again some positive but less slope. And this requirement implies in 1 dimensions that the slope is always non-negative of the gradient. All right, so that's the gradient property. And this is connected to, it follows quite easily from this first order condition for convexity that maybe some of you have seen. So you can also see in Stephen Boyd's book that the function is differentiable, or sorry, that a differentiable function f is convex if and only if this thing holds for all choices of x and y. And one way to interpret this is that assume that we fix an x. So here we have fixed the x at this point. Then we construct the function that is on the right-hand side, this one, which is this line here. Because if now we have fixed x, so f of x is a constant. It's here. Gradient f of x is the slope at this point, then times y minus x. So these two form another constant. And then gradient f times y is linear, which means that this function is affine in y. And for all y, it should be below f of y, which is the original function. So f of y should be greater than or equal for all y than this affine function in y. And these are for all x and y. So we can linearize at some other point x. We can pick this point x here. Then they touch at this point. We get a linear function like that touches the function at x and is below or on the function everywhere. So if we just change order of x and y, then this must also hold. Both these conditions hold for all x and y. And by adding these two together, just take sum of these two, we'll get exactly what we had on the previous slide. So this is what we get. So we can see very easily, once we know the first order condition for convexity, we can very easily arrive at this monotonicity inequality to show that gradients of convex functions are monotone operators. All right. But sometimes we have functions that are not differentiable. We saw that also in the previous talk, non-smooth functions. So here we consider functions that are non-differentiable but still convex. So non-smooth but convex. Then we don't have a gradient everywhere. We have it almost everywhere, but not everywhere. So most points in this example function has gradients, but at this point here, we do not have a gradient because we have a kink at this point. So in that point, we instead have a something that's called a subgradient. And what the subgradient does, a subgradient at x, it defines a slope. So defines the slope of an affine function that is a minorizer to the function. So affine function means that it's affine. Affine minorizer in this context means that the affine function, for instance, this is below the original function, and it touches the function at x. It touches the function here. So every subgradient at x defines an affine minorizer, the slope of an affine minorizer that touches the function at x. If the function is differentiable at x, the only subgradient that exists is the gradient of the function at that point. And if the subgradient is unique, the subgradient is also the gradient at that point. But for points where the function is not differentiable, the subgradient is not unique. There are several subgradients at that point. So we see here we have two lines, this line and that line, and both are affine minorizers to the function that coincide with the function at the point x, where this is x now. But they have different slopes, so which mean that they correspond to different subgradients. So if you compare to what we had on the previous slide, we had f of y greater than or equal to some affine function. The only difference here is that we have replaced, here we had the gradient before, now we have s, which is the subgradient. So this function is, the full function is f of y. This is f of x plus s1 transpose y minus x. This one, f of x plus s2 transpose y minus x. So here we have s1 and s2 that define the slope. They multiply y, they define the slope of these affine minorizers. And they are different, s1 and s2. And the notation that we use for subgradient is this partial symbol. So the subdifferential at a point x is the set of vectors s such that this holds for all y. So the subdifferential is a set, and the subdifferential operator takes a point in Rn and returns a set in Rn. This is a notation for the power set, which means the set of all subsets of Rn. So essentially, to summarize, subgradients define the slopes of the affine minorizers to the function that coincide with the function at this point x. All right, so again, using the same trick as we did before, using f of x, just swapping the meaning of x and y, which also holds since it holds for all x and y, and adding these two, we get this thing. Here I have use notation u and v instead of s of the previous slide. So we have a convex function. Then the subdifferential is monotone, which means that for all subdifferentials u at x and subdifferentials v, for all subgradients u at x and subgradients v at y, we also have that this scalar product is positive. So in this case, we still have the interpretation the angle between u and v and x and y should be at most 90 degrees. So we have this, and for all u minus v, the angle should be at most 90 degrees. But in this case, this holds for all differences of subdifferential at x and subdifferential at y. So we actually have a set that is fully contained in this right-hand side. And the difference in the one-dimensional case is here that we still have non-negative slopes, but as opposed to in the gradient case, we can now have also infinite slopes. So for this point x, for this point x naught, all of these points are subgradients, or all of these values are subgradients to that function in R. While if it would be a gradient, it's unique, and for those points we have not infinite slope, but still non-negative. All right, so we have seen that the gradient of a convex function is monotone, and the subdifferential of a convex function is also monotone. So what is a monotone operator? A monotone operator is exactly an operator A that goes from Rn to a set in Rn, or to the power set. And it's monotone if the scalar product that we have been talked about for all u in Ax and all v in Ay is non-negative. So we have the same picture that we had all the time, x minus y. And the scalar product should lie in this half all the time. So essentially, the point I want to make is that if you're familiar with gradients of convex functions, you can think of the monotone operator as the gradient of a convex function. If you're familiar with subgradients of convex functions, you can think of the monotone operator as that. But it is more general than that, and we will use this generality for some of the algorithms. But you can keep in mind that it is roughly the gradient or subgradient of a convex function. But then there is one more monotone operator that's very important in optimization, and that's probably quite easy to grasp what it is. And it's called a skew adjoint operator, linear skew adjoint. We can go to the definition essentially. So if it's linear, bounded linear, and satisfies this thing, so it's single valued, so we can replace essentially the u by ax because we have equality here, and v by ay because it's single valued. So we just replace u and v by ax and ay to get this scalar product here, and that this is equal to 0. If this is equal to 0, where a is linear, we have a skew adjoint operator. So essentially this means, if we go back to this slide, is that the scalar product is equal to 0 if the two vectors are perpendicular. So ax minus ay. So ax minus ay will end up somewhere on this hyperplane, which is completely perpendicular to ax. Yeah, so that's another operator that is important. One example is this operator that is 0 on the diagonals and 1 and minus 1 on the off diagonals. So it's essentially, when we apply it to x comma y, we flip the order and flip the sign of one of them. So we get minus y comma x. This is one example of a skew adjoint operator. And this is especially used a lot in primal dual optimization, first order optimization methods, where you try to solve these primal and dual problems at the same time. And this monotone operator is actually quite a powerful generalization of subgradient of a convex function, which can be used to, once you get over the more abstract formulation of this or construct of these operators, it can actually simplify analysis quite a bit. All right, so I've introduced the monotone operators as a generalization, essentially to gradients and subgradients. So let's look at problem formulations and their properties. So here we go again, try to connect the convex optimization with the monotone operator word to see that it's a slight generalization of what we have in the optimization word. So often these first order optimization methods like the proximal gradient method and ADMM and Chambol-Poc and so on can solve problems of this form where we minimize f plus g. And in this talk, we assume that f is convex, f and g are convex, and then they can have additional different properties than being just convex. And the reason why in this context we divide them into two terms is that we treat the two functions differently and individually in the algorithms that solve these problems. Now, if we have a constraint qualification, we won't go into details on what that is, but essentially always solving this problem is equivalent to finding a point x such that this holds. And this says that 0 should be in the subdifferential f of x plus subdifferential g of x. And again, we have a generalization of what we saw in the previous talk. If, for instance, g is 0, this is gone. We don't have g at all. And if f is differentiable, the subdifferential reduces to the gradient. And in that case, this inclusion problem just reduces to finding a point where the gradient is 0. So again, we have a generalization of finding of a first order optimality condition from differentiable problems to potentially non-differentiable problems. And essentially, if you think of it, if we ignore that there are two functions, we just look at one of them, and I can draw a convex function here like that. So essentially what happens is if 0 should be in the subdifferential of f at x, this means that we should have a fine minorizer with a slope 0. Slope should be 0. And then we can push this one up until we hit the function. When we hit the function, we hit this at some point x. And this by definition of a subgradient becomes a subgradient of the point x, which then, of course, since it's an affine minorizer and the slope is 0, is below all other function values, below the function value at all other points x. So yeah, if you look at the details and the definition of subgradients, I think you can convince yourself about this. It's referred to as Fermat's rule. All right, so essentially our optimization problem is equivalent in most cases to this inclusion problem, which involves subgradients and subdifferentials. And before we saw a generalization of the subgradients and subdifferentials into monotone operators. So instead of considering only monotone operator problems that come from convex optimization problems, we directly consider the more general monotone inclusion problem. And we write it as 0 in ax plus bx. And the objective is to find an x such that this inclusion holds for all monotone holds for the monotone operators A and B. And the plus here, I didn't mention that, is set addition. So AX, for instance, gives you one set, and BX gives you another set. And then when we take AX plus BX, we take set addition of these two, So adding all the individual elements in all combinations. And if 0 is one of those, we have found a solution. So essentially, if AX is here, then BX is here. We can take that point and that point, add these, and we will get 0. And that will be a solution. All right. So we have seen that convex optimization problems become monotone inclusion problems, but there also exist monotone inclusion problems that are not constructed in the way we just did, directly from convex minimization problems. But certain convex concave mean max problems can be rewritten as monotone inclusion problems. And also monotone variational inequalities can be written as monotone inclusion problems. And also some primal dual optimization formulations that I have been mentioning a few times can also be written as monotone inclusion problems, and they use a linear skew adjoint operator as well, which is not a gradient of a convex function. So it cannot be handled directly without using this monotone operator framework. All right, so again, why do we separate it into two? So if we write it 0 in AX plus B, why don't we instead write it at 0 in A plus B X and then define this as C or whatever, so we get 0 in CX? Why do we need these two different operators when we can actually phrase the same problem with just one? And the reason is just for notational simplicity, because first of all, we may have that A has one set of properties and B may have another set of properties. So both are monotone or actually maximally monotone. We won't go into what that means, but this is typically a crucial property that it's also maximally monotone, not only monotone. But everything that we will see here and have seen are maximally monotone, essentially. But then we need to add that the function is proper closed and convex, and then we get maximal monotonicity. All right, and in addition to that property, we can have that B is, for instance, Lipschitz continuous, cocoercive, which I will discuss next, or linear skew adjoint that we have been seeing a few times. And these operators A and B, first of all, they are maybe treated differently in the algorithm. So you could take you can perform different types of operations on the two operators in the algorithm, and also they are treated independently. So you never do operations on A and B at the same time, but you do perform operations on A and B individually, and then you try to add up on some things so that the algorithm that you have will converge. And sometimes we split into even more operators. If we have 3 different operators or 4 with different properties, we can split them in to that many operators sometimes, and also treat all of them differently and independently. All right, so I mentioned Lipschitz continuity and cocoercivity just before. And I guess that all of you have heard about Lipschitz continuity. And essentially, if we have Lipschitz continuities Tx minus Ty, you saw it also in the previous lecture. We saw the function was smooth, and it came from that the gradient is Lipschitz continuous. And this is a definition that this holds for all x and y. And if L, in this case, L is maybe 0.8. So this means that if x and y is here, then Tx minus Ty is somewhere within this gray region. So depending on the L that I had before, the gray circle grows or diminishes in size, and we are more or less sure on where this Tx minus Ty vector is. All right, and this can be compared to what we had before with monotonicity that looked like that. All right, and we can also see that the Lipschitz continuous operator is not necessarily monotone, because if Tx minus Ty ends up here, it's does not satisfy the monotonicity definition and is can therefore not be monotone. So if we want the Lipschitz operator to be monotone, we need to assume that separately. Okay, and then we can go over to cocoercive operator. So if we have Tx x minus y, sorry, then we have Tx minus Ty somewhere in this gray region. And we also have a parameter here that can scale for different choices of the parameter. The circle has a different size, but okay, this was not good, but it's always contained in the right-hand side. Oops, so this drawing is good enough. We see that actually the cocoercive operator is already a monotone operator because of that. And we also see that the cocoercive operator is Lipschitz continuous. Oops, because Tx minus Ty, hard to draw circles by hand. Tx minus Ty also ends up within this Lipschitz continuity circle. So cocoercive operators are Lipschitz continuous, but the way around does not necessarily hold. So for instance, skew operators that can be what we had before can end up here and here, which will not be inside the cocoercivity circle. But what is, if you have seen some analysis of the proximal gradient method or the gradient method, it's often assumed that the function is smooth, and then we say that the gradient is Lipschitz continuous. So Lipschitz continuity is this, but if the function is convex and the gradient is Lipschitz continuous, the gradient is actually also cocoercive. So we get these two properties combined gives us a stronger property of the gradient than just Lipschitz continuity. So for gradients of convex functions, Lipschitz continuity and cocoercivity actually coincide. So if we have the gradient of a convex function will always end up within this, I mean, the grad fx minus grad fy will always end up within here. While in more generality, the two properties are different. All right, so now we have, hopefully I've explained to you the problem setting, that we look at monotone operators, their definition, roughly what they mean, and then the problem properties, problem formulations that we're interested in solving, and the properties of the different operators that can be involved in these problems. And so now I will just fairly quickly go over some existing algorithms from the list that we had before. And there I call them primitives. Maybe it's not the right word, but I call them primitives. And this means that what is the basic computation block that is used in these algorithms. And many of these algorithms you have already seen in the previous talk. So what are the primitives? For convex optimization problems.
Hello. Pontus, yep. There is one student raising his hand. Yes,
Oh, okay. Sorry about that. I didn't see it.
Yes,
please
hello.
Go ahead, Jester, if you have a question.
Yes, I have a question to slide 11.
11, yeah.
For the conditions of optimality.
Mhm.
So the goal is to minimize the sum of both functions, f and g.
Yeah.
And I read the optimality condition now as follows. If I have a point x that satisfies that the subgradient to f is equal to 0, then that is already, it's only a necessary condition. Or is it? No, it's necessary and sufficient, right? So then my question is, if I have a point x with subgradient of f at x equal to 0, would this then completely ignore the function g?
No. So the x that you have connect the subgradients at both f and g. So essentially, you need to evaluate the subgradient. Maybe take the full set that you get from here. So this is a set, and then this is another set. Then you can look around everywhere in these sets to try to find vectors so that the sum of these is 0. So one is minus the other, essentially. So
okay,
I think maybe I can draw a picture. Let's see, on top of my head. Okay, maybe this will not be a good one. So if this is f and this is g, let's see. No, I think we should have a different. I think it will be difficult to draw, but essentially the way one can see it is that, I mean, if you have a one-dimensional function like that, then you have another one-dimensional function like that, then you can see where the slope, I mean, these are differentials, these are just gradients now. So these define slopes over fine minorizers. If the slope of one, say that the slope of this one is SF, if this is F and this is G, and the slope of this one is SG, and if SG equals minus SF, so that they actually point, they have the opposite, then this condition will tell us that this is the optimal point. Because then 0 equals SG plus SF.
okay.
And if you add these two figures together, hopefully it will have its minimum somewhere here. I don't know how it will look, but.
Yeah, I think then my problem was that I did not fully understand what the plus sign means here. You drew two sets earlier, and
yeah.
I thought it was just taking the union of two sets, but it said, could you explain again what it is?
Yeah. So what the plus sign means is that you take, to form this, the result of this is a set. We have an inclusion. So this is a set. And this is the set of, maybe I can write it, u plus v such that u in subdifferential f of x and v in subdifferential g of x.
Okay. So
essentially you take u1, u2 here, and then I don't know if origin is like that. Take this vector and that vector and add them. And this becomes one object of that set. And then you take this vector and that vector, add them to get another, and this and that one. Okay. So it's called the set sum or Minkowski sum.
Yeah. Okay. Thank you.
Okay, good. Thank you for the question. All right. Please don't hesitate to interrupt me if I don't see the raised hands in the chat. I will try to, or in the list. I will try to keep an eye open. All right. So the algorithms that I listed earlier, and that many of these you saw in the previous talk, they use if the gradient is convex smooth or only smooth, like in the previous talk. Typically, the gradient of that function is used. but if it's non-smooth, so that there are non-differentiable points, you typically need a diminishing step size in order to deal with subgradients directly. So in a sense, you compute subgradients via the proximal operator that you saw, that solves this optimization problem to compute the proximal operator output. And sometimes this is quite difficult to solve depending on what f is. So when we do this splitting, I don't know where we had, when we do split the mean f of x plus g of x, we try to split the problem in f and g so that the computation of gradient and computation of prox are cheap, both of them. Or that they grow gracefully with problem dimension. So what essentially all these methods do, maybe not all of them, is that they combine using the gradient of f and then the prox of g, or in some other combination, to arrive at different algorithms to solve these problems. And if we instead go to the more general problem formulation, which is a monotone inclusion problem, we can essentially replace, if a is single valued, we can replace the gradient by just evaluation of a. And if a is not single valued, so it is set valued, meaning that it can output not only singletons, but many points at some places for some x, we use the resolvent, which is defined as this. I don't know if you're familiar with this notation before. It's called a resolvent applied to x. And actually, if we have ID, this is just an identity operator. For input x, it gives an output x. To connect it to what we had above, we have this relationship. So, I mean, the optimization problems are phrased in terms of functions, convex functions, and so on, which you have, you have an input domain, and then you have an output domain in R. So Rn input, for instance, and output R. While these inclusion problems, we don't have this notion of functions. We only have input dimension Rn and also output dimension sets for single valued also in Rn. But the connection between resolvent and proximal operator is that if we plug in the subdifferential of f in place of a in the resolvent definition, then we get exactly the proximal operator of f. So this is just a pure generalization of the prox that holds also for monotone operators. So we will stick to that notation mostly. And then we can also do a scaled version of the resolvent. It looks like this, where S is, in Rn, it's a positive definite matrix, essentially. And essentially it's, to have this is actually equivalent to having this, but applied in a different, the Hilbert space with a different inner product and different norm. So we actually don't need both of them, but for simplicity, I have added both. So these are, for the problems that we saw, these are the building blocks or primitives that are used in all these methods, essentially, maybe apart from one or so. Okay, so now I will just list them so that you see that I am telling the truth, let's say. So proximal gradient method, you saw it. We minimize this composite sum. F is smooth convex, G proper closed convex. It doesn't have to be, it can be more less restrictive assumptions, but the algorithm is given by this. We have the gradient and we have the prox. So we use prox and gradient. And the more general method then is forward-backward splitting. So now we solve monotone inclusion problems. We have seen that the monotone inclusion problem that we had is a strict generalization of that problem. And the properties that we had F smooth convex, G proper closed convex. This corresponds to the G part, corresponds to that A is maximally monotone, and that F is smooth convex corresponds to that the gradient of F is Lipschitz continuous, and since F is convex, it implies that the function is, or the operator is, the gradient is cocoercive. So this is also a direct generalization of first we go to this equivalent problem, and then we take the properties. This is maximally monotone. No, this is maximally monotone, and this is cocoercive. And then we get rid of the assumption that it comes from a function, to just state it in a monotone operator word. So this is a pure generalization. Then the algorithm is the same. You can think of this. This is the prox with some step size gamma. So it's the resolvent. And here you have the, you can think of this as the gradient. So we have a gradient step, which is called a forward step. So here is the forward step. And then we have the resolvent step here, which corresponds to the prox step, and it's called a backward step. So forward, backward. And the primitives are then the resolvent and just evaluation of C. And this is just a pure generalization of the previous problem into the monotone operator world. And then in the previous lecture, we also saw Douglas-Rachford splitting for convex functions. It can also be applied to monotone operator problems. So again, we have this problem, and here we don't have any additional assumptions on smoothness, but A and B are just maximal monotone, which is the basic assumption that we need here. And the algorithm looks like this, quite different from the method we had before. And the primitive is the resolvent of A and resolvent of B. These are the primitives. Here we have a Chambol POC that I mentioned. It can solve problems of this form. We have some additional structure. The reason why we explicitly involve L here is that this will, in the end, be evaluated via multiplication and not be part of any prox or resolvent. So this is the basic problem that we want to solve with that method. And it can be shown that this is actually equivalent to that thing here. I will not go into details, but I can just give you a hint. I'll write it like, okay, I'll write it star, subdifferential G of Lx. So this, if we do the same trick, or if we do the same optimality condition with some constraint qualification, so say that this is equivalent to that, where this is the subdifferential of that function, which is G composed with L. Maybe I can make this one. Okay, like that. And then we call this thing Y. Then I think you can read from this first line, subdifferential f of x plus L star Y. And then we have in addition that this is Y. So Y equals subdifferential G of Lx. And the only difficult thing on top of that is that we need to use a result saying that this is true. That these two are equivalent. And here we have gone from the function G that the problem is formulated in to its conjugate, to dual conjugate function, G star. So the G star ends up here, and then we move this to the other side and have 0 here. So we get the second line. I don't want to go into the details. If you didn't follow, it's fine, but you need to use u in subdifferential g of x is equivalent to x in subdifferential g star of u. And apart from that, it's just going directly from the optimality condition. And it turns out now that this is a monotone operator. We only have a product of subdifferential operators, so this is monotone. And here we have a skew symmetric operator k, which is not the gradient of some function, but it's still maximally monotone. So here we can actually apply the algorithms we have for maximally monotone problems to this inclusion problem, while this would not have been possible if we wouldn't go to the maximum monotone generalization. And the algorithm that is called the Chambol-Poc algorithm actually takes A and K. So let's say bold font A, bold font K. We let them be just some A. And we take a resolvent with some S. You saw the scale resolvent that we had is S plus A inverse S times that thing. And the S that we have is of this form. It's a symmetric positive definite matrix depending on tau and sigma. So there are some conditions for this with positive definite. And once these conditions are satisfied, this is just a pure resolvent method that will converge. And if we do the algebra here and do some simplifications, we will see that we get actually a block triangular update rule. And in the end, we will only have procs and evaluations of L. So we still have the same basic blocks once we write out the algorithm on more specific form. But I have not done that here. All right, so this was another example. Now I would like to go to forward, backward, forward splitting. We solve a monotone inclusion problem. B, maximal monotone. D, Lipschitz continuous. The first step is a forward, backward step that we saw before. And then we have an additional step here that we didn't have in forward, backward splitting. And the reason is that D is Lipschitz continuous. Lipschitz continuous instead of cocoercive. Cocoercive, this is cocoercive, and this is Lipschitz. In cocoercive, we didn't need this extra step, but now when D is Lipschitz continuous, we need to have some type of correction step to have convergence. But again, we have the resolvent, and then we just evaluate D, the single value, we just apply it. And in this time, we need to apply it twice, once to xk and once to x hat k. And then there is a generalization of this, which is called Malitsky, we call it Malitsky-Tam. It solves the same type of problems, but instead of doing that specific correction with the second application of D, they have a forward backward step, but then add a specific momentum term to it, which is essentially the difference of dxk and dxk minus 1. So there is some momentum term here that is added to the algorithm, and this also converges to a solution of that problem. And we have resolvents and D. And here we have two applications of D in every iteration, but since it's applied to xk and xk minus 1, one of them can be reused. This one can be reused from the previous iteration. So therefore, we only have one D evaluation per iteration instead of two. All right, and now we're at AFPA algorithm. It has three operators, maximal monotone B, cocoercive C, and linear skew adjoint L. And this algorithm is a bit different. I will not go into the details, but it has a different resolvent than what we have seen before, because Q is positive definite, like the S we have seen before, but we have an additional K here, which may be linear and skew adjoint. And then the algorithm looks like this. So this is slightly different because it uses a non-symmetric scaled resolvent instead of the standard resolvent that we have seen everywhere. And this is one of the motivations behind our work. And we will come to this after the break. So what we will present then is a framework that unifies these methods that solve monotone exclusion problems. And it will be based on something that we call a nonlinear resolvent that we will introduce right after the break. So let's see how much time is there left. It's 50 minutes left, right?
Yeah.
Yeah,
Yes.
something like that.
Yeah. Yeah.
So if we have a 7-minute break and resume at 3:45, I think that would be quite good. So yeah, okay. Let's resume at 3:45. And if you have questions in the meantime, I will stay here. So you can just unmute and ask if you want. Right, see you soon. All right. So next part will be on, let's say, the new things. So I will try to connect this to what we have seen already and to see how this generalizes what we have seen and what the challenges are with the new definition of the nonlinear resolvent. And again, the overall goal is to have one, actually it will be two algorithmic schemes that have all these other methods as special cases to hopefully provide some extra understanding of these methods. All right, so in the algorithms that we will present, we have one unifying building block. We have one building block for that. And this extends essentially the resolvent that we have seen so far. So we saw that all these methods that we listed before use this standard resolvent, and there are many reasons for why this is a good object for monotone operators. So one is that this is non-expansive, this operator, and it has even stronger properties than that are very useful in algorithm analysis. And we have seen that the proximal operator is a special case if we consider monotone operators that are subdifferentials of convex, proper closed and convex functions. All right, so we have seen that one. In the previous lecture, you actually saw this resolvent. You saw the Bregman proximal operator, and you had this argmean of something like this, plus, and for the standard, plus. And then instead of having 1 over 2, 2 norm squared, you had some Bregman distance in terms of h. Something along these lines is what you saw, but this is taking such a step is can be written, is equivalent to doing this operation. So instead of having the identity operator here in the resolvent, we have the gradient of some differentiable and strictly convex function. It can be, there are many technical details in this area, but this is one assumption. And when we have this, we need it also in that part. So we first apply the gradient of h, then we take that result and apply this type of operator to that. And the generalization that we have is called a nonlinear resolvent. We know that gradients of convex functions are monotone. So what we do here is, instead of restricting ourselves to gradients, we take the full generality and use a monotone operator. And we will see that this is needed in order to arrive at some of the special cases that we listed before. And we call this M a kernel. And this is a single-valued maximal monotone operator that is typically strictly monotone, meaning that it satisfies the monotonicity inequality with strict inequality, essentially, and also Lipschitz continuous. And we put out a paper with this construction, and we call it nonlinear resolvent. And at the same time, it was introduced what's a typo? Warped resolvent in another paper by some other authors. but we call it a nonlinear resolvent. And it's a strict generalization of this one, because identity operator is a monotone operator, maximal monotone operator. Okay, so what we saw is that if we iterate the resolvent with a positive definite or identity operator, we'll actually have convergence. We saw the Chambol-Poc method was defined like this, and we had a forward-backward method. If we just take the backward part, we also have just a resolvent iteration, and both of them converge. While if we take this non-symmetric or nonlinear resolvent, non-symmetric nonlinear resolvent, we may not converge. And one example is if we do this for 0 in AX, or actually since A is single valued, we will want to find an X such that 0 is equal to AX. So one obvious solution, since A is linear, this is A, this is just a matrix, is X equals 0 is a solution. But for all other values of X, it will not happen. It will not be a solution. So X equals 0 is the only solution. And now we construct a kernel M, which is of this form. So we take identity minus A. And this is actually a trick that we will see later again, just to take minus the operator that we're interested in. So if we apply that, okay, I forgot xk here. If we apply the nonlinear resolvent to this problem and with this M, we have M here, M here, and M here. Then the parentheses, this actually becomes identity, and I inverse is just identity again. So the only thing we have left is this. And if we write that out, we have identity minus A. Okay, so we should actually have flipped these two probably. All right, and if we look at this, is just a pure matrix iteration, and it's a 26-degree rotation and a 1.12 amplification. So in every iteration, we are 1.12 further away from the unique solution 0 than we were before. And if we iterate this a few times, we get a trajectory like this, and this will be spiraling outwards because of the rotation and amplification. And it might be that it's actually spiraling in the other direction. There might be a sign error somewhere, but this non-symmetry, it's still linear. M is linear, A is linear, everything is linear, but the non-symmetries in M can actually make the iteration be not convergent. So there is a problem with having non-symmetric M. So for instance, if when we are in this setting, the gradient of H is nonlinear, but it's always symmetric. So symmetry, so if it's not symmetric, we need to do something to ensure convergence of the method anyway. We will get back to that. And first look at what if we instead choose a symmetric M. So we take it to be the identity, which gives us the standard resolvent. I forgot xk here again. We have the same problem, and we do the resolvent method, but now with identity matrix. The resolvent looks like this, which is the pure standard resolvent that we have seen in most of the algorithms. And if we do the computations, we get that matrix, and it's still rotation with the same number of degrees, but now it's the amplification is less than 1. So the length of the vector is reduced, and we spiral inwards towards the solution. So in this case, it helps us to symmetrize M. So the question is, why is it not always symmetric? Why don't you always choose M symmetric? I would say that if it's possible, it's probably beneficial to choose M symmetric. And this is the case, for instance, for forward-backward splitting, Douglas-Rachford splitting, Chambord-Poc. But then there are some other methods that, if we translate them to this framework, have nonlinear or non-symmetric M, and they have other benefits. They have some benefits. For instance, it can be cheaper to evaluate, or it can be more easy to parallelize, or something like that. But this talk is actually not about saying how to choose M and what is preferable. The purpose of the talk is to unify these apparently quite different methods in a framework. Yeah, this is the purpose. So I'm not advocating to have a symmetric or non-symmetric M. It's more trying to describe what the current status is for methods in large-scale convex optimization. All right. So with that said, we know that we cannot just iterate this nonlinear resolvent and expect to have convergence as opposed to with the other methods. So is it useful at all? So one key feature is that it defines a separating hyperplane between the point where we apply the nonlinear resolvent and the solution set. So if we define x hat k to be the output of this nonlinear resolvent, and then based under some assumptions on M, such as strong monotonicity, for instance, or strict monotonicity, we have, if we define half space, hk, so a half space, like this. So we take all the z's such that this is less than or equal to 0. And this is a half space because we have c here. This, for given xk and x hat k, this is just a constant, the combination of this and that difference. And then we have a scalar product between a constant vector and z. So this is just a normal to this hyperplane. So mxk minus mx hat k. And then this part decides where this exactly this hyperplane is placed along this normal. All right, so what does that mean, that it's a separating hyperplane? One thing we know is that h hat k is on the boundary, sorry, x hat k is on the boundary of hk, so x hat k is somewhere on this line. And we know that all solutions to the problem we want to solve, when we have, if we iterate this, the problem is 0 in ax, and all solutions are in hk. So here are the solutions to the problem, and the point where we apply the nonlinear resolvent is not in hk, so it's somewhere outside. I mean, for a half space, you can either be inside or outside, let's say, if it's a point. And it cuts the space in two halves. So now we have cut the space in two halves, and we know that we have one point on one side and the other point on the other side. And the point xk is strictly on outside, let's say, the half space. So we have what is called a strict separation between xk and all solutions. And before we go on to see how this can be used, we introduced a nonlinear forward-backward map. So what we had before was just the nonlinear resolvent for a maximal monotone operator A. But we will be interested in solving these types of problems where A is maximally monotone and C is cocoercive, which implies single valued. So now we will combine the similar way as we have for if we would have had if S here, this should be minus. If S would be positive definite, let's say in Rn, if we solve a problem in Rn, then this would be the forward-backward map. And the generalization to our setting would be this, where M is, the kernel M is potentially nonlinear, maximally monotone. So if C is 0, we get back the nonlinear resolvent. If M is ID, we get back the standard forward-backward step. So this will be the basic algorithmic block when we solve problems of this type. And we have exactly the same property as for the pure nonlinear resolvents. So beyond maximal monotonicity of A, we assume that C is cocoercive with respect to some norm. We define a half space like this. We have the same thing here, but instead of less than or equal to 0, we have something that depends on the cocoercivity constant and the cocoercivity metric that P is defined, C is defined in on the right-hand side. But given this half space, we have exactly the same properties. X hat k is on the boundary. All solutions now to AX plus CX are inside HK. HK is this full thing. And the point of application X is outside. So again, we have strict separation between XK and all solutions. And of course, since one special case of this is that C is 0, and a special case of that resulting thing is that we have no convergence if we iterate just this thing. We cannot expect convergence here. So we need to have some type of correction in order to have convergence. So let's see how we do that. All right, we have two different types of correction. So one will be a projection correction, and one will be a momentum correction. And the reason why we have these correction methods is that we need to compensate for nonlinearity and non-symmetry of M. This is what we saw in the example where we can diverge by just iterating this object itself. So we need to correct for nonlinearity and non-symmetry. All right. So the first method that we have is the one with a projection correction. So again, we solve problems of this form, and the method is given here. This is the first step that I talked about, the nonlinear forward-backward map. And these two last steps, you can recognize probably this step. This is what we just saw. This is the definition of the half space that contains the solution set but does not contain xk. So this is the second step, and the third step we project onto that half space. This is the projection, and perform a relaxation. So essentially, with the relaxation, I mean, so what this method does is essentially we take a step like this, we construct hk, and we find x hat k, and then we project onto that. This is pi hks xk, and then we do a relaxation. There was a factor theta, I will show again. This is a relaxation where we can come anywhere on this line in between xk and twice as far into the set compared to the projection point. So the projection decides if we are here at 0 or here at 2 or here at 1. It's a projection and then a relaxation on top of that. The relaxation parameter is this theta k. So if it's close to 0, it will be close to xk. If it's close to 2, it will be almost it will be essentially reflected on the projection point into the set. And if it's 1, this thing disappears. This is 1, and we get only the projection. So let's now look at what are the computations required for this algorithm. First, we do a forward-backward step. For that, we need to apply mk to xk. So we need one such application. And in order to construct this hk, we also need to apply mk to x hat k. So we need to evaluate mk at 2 different points in the space. And the way we can prove convergence for this is that since we have a separating hyperplane and we project onto that, we know that we will not get further away from a solution. If you think of, if you have a point, have a separating hyperplane, and you project onto that, and you know that the solution setting is on the other side, you will actually not be further away from the solution set than you were before. And if you repeat this, you know that your distance will not increase, at least. And if you go deep enough, let's say if the steps that you take are long enough, you will in the end converge towards a solution. And it can be shown that an inequality of this form is satisfied for some positive psi and all solutions z under some assumptions on all the mk. So how can we think of this? We see that this is the distance to the solution at xk plus 1. This is the distance to the solution at xk. We see that at xk plus 1, the distance is smaller, or distance squared is smaller than the distance squared. And then there is a quantification on how much smaller it is as well. And this is called phasor monotonicity, and it's a very common tool to prove convergence of these types of methods. It was also mentioned in the previous talk, and it can be used, this thing can be used via some more or less standard steps to show convergence of this method. So to do a projection correction, once we know that we have a separating hyperplane that generates deep enough cuts, let's say, that makes enough progress, we can show convergence like this. But the method with momentum correction has a bit more involved convergence analysis. We solve the same types of problems. We have the same assumptions. Instead of doing projection correction, you see that we have the same forward-backward step here as we had before, nonlinear forward-backward map. But then we have a correction term that enters inside here. And this correction term is a momentum term that actually compares gamma k mk and s, gamma k mk and s. So the more different gamma k mk and s are, the bigger the UK correction term will be. And the same case is a positive step size parameter. Yeah. So what we see here is that we actually still require 2 evaluations of mk per iteration. We evaluate on xk, but we also evaluate it on xk plus 1. But in the next iteration, so yeah, we have these evaluations, but in the next iteration, we will evaluate this, but it's very often cheaply computed from that we already have from the previous iteration, which means that most often we only need 1 evaluation of MK per iteration, while in the previous algorithm with projection correction, we needed 2. And this MK can be, depending on the algorithm, it can be quite costly to evaluate that one. So it might be good to avoid one application if possible. And as you see here, the Lyapunov analysis is a bit more involved. We have one quantity here, which we can call VK plus 1. We have the same quantity here, VK, but one iteration index lower. And then we have a third thing here, RK, which says that VK plus 1 is less than VK, unless RK is 0. And RK is positive, so we have some decrease of VK. And we have this if we assume that all these gamma k mk minus s are Lipschitz continuous, and that this term is strictly positive, we can use these to show convergence of the method. But we will not go into convergence analysis. Just want to show this merely to say that the momentum correction algorithm is a bit more involved to prove convergence for than the projection method, which is a bit more straightforward after you know the fact that the method creates a separating hyperplane. All right, so we have introduced this nonlinear forward-backward operator. And we have seen that it will not converge if we iterate it just purely without any correction, or it may not converge. So we can't have that as an algorithm. So we needed to introduce some correction. So we have projection correction and we have momentum correction. And what happens in these two methods with projection and momentum correction, if we let all MK be linear and symmetric, and in particular, we select this choice, you perform this choice for MK. So gamma k m, or gamma k mk, is then equal to S, where S is the metric in which we perform projection. So when we do projection, we have minimize C minus X in C. And here we can choose metric, which means that we choose the norm in which we perform the projection. And this is free to choose in the first projection method. And we call it S, the matrix that defines this metric. And if we look at the momentum correction method, we had this UK term that involves two terms that multiply this operator. So with this choice of gamma km, UK is equal to 0 for the momentum method. So in both of these methods, what the resulting thing will actually be, it's easiest to see in the momentum method, but for the projection method, it's actually the same. And the resulting method will actually be just a standard forward-backward splitting method. So this means that if the metric that we choose is linear and symmetric, then we can choose the S. We can choose it in such a way so that, okay, this will also have to be iteration independent, but then we can choose things in such a way so that we actually get back to forward-backward splitting. So essentially what we can see from that is that these algorithms with the correction methods, they actually the correction only kicks in if it's needed. So if we have nonlinearity or if we have non-symmetry, that can cause instability or divergence of just a pure iteration. then we get the projection correction will help, or the momentum correction will help. While if this is not the case, if it's linear and symmetric, the correction methods are actually nullified, and we get back to the basic forward backward splitting method that we know converges. So this is actually quite neat thing to see. All right. So we mentioned a list of special cases initially. So now we have our two methods that are based on the nonlinear resolvent. And we see here special cases. If it's bold font and italics, like these three, it's a special case of both methods. And the reason is that these are a special case of forward backward splitting. And if it's only italics, it's a special case of the momentum method. So these two are special cases of the momentum method. And these three are special cases of the projection method. Yeah, and we will go into two examples of this. But first, actually now I am coming to the trick that is used to arrive at this, most of the special cases that are not standard for backward splitting. There is a specific trick that is used in all of those cases that we have seen, and I will show it to you here. So now we assume that we want to solve a problem of this form. We have B is maximally monotone. No, sorry, we have B plus the sum of all these di's is maximally monotone. One way to ensure this is that all of the individual operators are maximally monotone, but we actually don't need it. It's enough for the sum to be. And then we have C to be cocoercive. And then all these di are single valued, and they can have different properties. And two examples we have seen are skew or Lipschitz. And the special cases we have seen all follow are all on this format, with some of the operators being zero. So this is the problem formulation. I copy the problem formulation to this slide to the left here. So this is what we want to solve. And our algorithms that we have, the projection and momentum correction methods, solve AX, 0 in AX plus CX. And then we can follow the following recipe to get actually all the methods that we had in the previous list. And they're all obtained in the following recipe. And actually, we have only found, we actually derived one new algorithm that is constructed in a different way than this. But apart from that, we haven't seen a different construction. All right, so what we do in order to connect these two is that we say that B and this sum, we add these and put them in A. So we let A be this sum, and then we just keep the cocoercive term C as it is. All right, so now what we do in the forward-backward step here, in the resolvent step, is that we set MK to be sum QK. This is to be chosen. This is linear, symmetric, self-adjoint, positive, strongly positive. So it's we can say it's positive definite matrix. And then we have an additional K, which is Q symmetric. For instance, K can be 0. So these two are chosen when you design the algorithm. But apart from that, we subtract all the di's from MK. So we need to select, now since we subtract all these single value di's, we need to subtract or select QK so that the properties required for MK, such as monotonicity, are satisfied. Assuming we have done so, select Q, K, and K so that the properties hold and we get cheap updates. We see that the nonlinear forward-backward step that looks like this, actually when we evaluate it, can be evaluated of this form. So even though A involves B and D, inside the invert, I mean, this operation can be difficult if we have lots of summands here, but by just subtracting everything, we see that MK plus A, we first add all these D's in A, and then we subtract them using M. What happens then in practice is that we move all the DI's from inside the inverse here to the so from the backward part to the forward part, so from this part to that part, which means that we only need to evaluate the DI's by applying it xk to DI. We do not have to evaluate it inside this inversion or this resolvent. That may be very difficult. So this nonlinear resolvent, we can assume that K, for many algorithms, K is 0, so we can assume that this one is gone. If we in addition set QK equals to identity, this would be identity, this would be identity. You see that we have a pure forward-backward step, where the backward step is on B, and the backward step is on B, and the forward step is on all the D, I's, and C. But then there might be reason to select Q differently than ID and K differently than 0. And the choice is essentially to have cheap updates. We essentially want to choose K and Q to have cheap updates in the end. This trick of M made it cheap because it allowed us to move the difficult D stuff from one side to the other. And then Q and K is to get the rest cheap as well. And now when we have decided how the forward-backward mapping should look, we can choose to either do projection correction or momentum correction on top of this to get a convergent algorithm. So if we look at the forward-backward-forward method I mentioned before, we solve these types of problems. The sum is maximal monotone, and D is Lipschitz continuous with constant L. We have seen the FBF method briefly. We have a forward-backward step, and then we have some correction that involves an extra evaluation of D at x hat k. And this algorithm can be obtained from NoFob with projection correction. And the other method, Malitsky-Tam, we have a resolvent.
There is a student raising her hand.
Oh, sorry, yes. Sophie, yes, please, go ahead.
Hello, I have a question regarding the slide before.
Mm-hmm.
So I see that the Q also has a K index, so it's updated with time. So does that mean you need to also design an update rule for Q? Or I guess because the K is probably fixed, or it seems like the K is fixed and the QK is updated each time. So I would be interested how to update this QK, or how do you know that then MK always fulfills the conditions depending on how you update QK?
Yeah, that's a good question. So actually both QK and K, both Q and K could be iteration dependent. I didn't mention it here, but they can also be fixed. But the important point is that they are completely user chosen. So you can choose them however you want. As long we have a list of properties that MK needs to satisfy for the two different algorithms. So as long as MK, which is this, satisfies that for all K, we could also add an iteration dependent KK. Then everything will work and we will have guaranteed convergence. And we can, for instance, choose Q to be also some fixed positive definite matrix as well.
So then I guess my question would be, what is the advantage of if you have a fixed set of assumptions that need to be fulfilled by M, why would you want to update M with MK if you can find one fixed one that fulfills all the assumptions? Isn't that like a lot more work to update it each time and find a QK that also updates it accordingly? Yeah,
I agree. I think in most cases in practice, you will actually have a fixed M. But we will see an example later where we have actually iteration dependent MK, but the only iteration dependence is a step size. If you look at this algorithm, there is no step size in the method. So to get forward-backward method, we actually have MK is gamma K inverse identity. So in that case, we will get forward-backward because it will reduce to gamma K can actually be moved to here. And then we can use an iteration-dependent step size if we want to. And sometimes it's beneficial because you could potentially do some type of line search or something else where you can define gamma in different iterations. But beyond that, I have not seen. Yeah, actually, we have one other algorithm in one of the papers where we have an iteration-dependent MK, but this is chosen. It's actually an iterate of the algorithm that enters into the metric in the next step. And that's the only reason. But apart from that, I think constant M is what you have in essentially all algorithms.
Okay, thank you.
Thank you. Thanks for the question. All right. So here we have the forward-backward step, and then we have some correction term. And it turns out that this can be obtained from NoFob with momentum correction. So if we just follow the recipe that we showed, we have MK to be this, and A is B plus D. We say we take B and all D stuff into A, and then we set C to 0 because we have no cocoercive term. If we evaluate this resolvent, we just plug in the M and A, and we see that these two cancel. And here again is the M. These two cancel, so we get that thing, and again the M. And then this is essentially what I tried to show on the other slide. Here we have gamma K inverse. We can just put out the gamma K inverse to get it on this form instead. And then we see that we have iteration dependence only in terms of the step size. So if we're happy with the constant step size, we also have a constant M. But again here, our nonlinear resolvent in the nonlinear M becomes a standard forward-backward step in B and D. And so without going into the details, we don't have the details here. If we do projection correction with a specific relaxation factor, we get this update for the projection. This is an explicit formulation for the projection. So forward is actually can obtain from this NoFob with projection with a very specific relaxation factor. And it's actually, yeah, it's one more, let's say, restriction that has been put into that before, even before this. I won't go into the details, but it essentially becomes a short step version of NoFob with projection. And then if we do with momentum correction and set STB identity, then the UK that we have, which is defined here, with the same choice of MK, will, if we just do the algebra, will give us this. And then this is exactly the Lipschitz time correction. So the two different methods we have seen for solving this B plus D problem can be found also as special cases of these two no-fob variations. But the key to getting there is to understand that this trick, we have A is B plus D, and then we just subtract the D from M to effectively take it from the resolvent side to the forward side. So if we look at that just from a computational point of view, it may look very expensive to compute, but since A involves B and D, but with this particular choice of MK, it is quite typically quite easy to compute because we assume that the resolvent of B is cheap and then that forward evaluation of D is cheap. All right, and we have seen that the algorithms coincide and they have convergence under the same. Our convergence analysis give the same conditions as the original FBF and Lipschitz papers. So I see I have over time with 1 minute, but I have my final slide here. So I hope it's okay if I go over this one again. It will be quite quick. So I wanted to mention also Polyak momentum. So essentially in Polyak momentum, we add the term of this form to the update equations. And what we get actually from our no-fob momentum algorithm, if we set the gamma k we had to 1 minus theta alpha k and do some very simple algebraic manipulations, we get this update rule. We get this algorithm. So we see that it's actually exactly the same algorithm as before, written slightly differently, but we have our momentum. We have a momentum term that pops up here. I mean, this is also a momentum term because it has xk plus 1 and xk. But here the Polyak momentum is s times xk minus 1. Not involving other operators. So we can explicitly take this one out and have the same algorithm. So essentially for free, we also get all the momentum methods, Polyak momentum methods, where there has been lots and lots of papers in trying to define those and analyze those Polyak momentum methods. And this is essentially for free with this involved analysis with no-fob momentum. So essentially we swap one step size gamma k for a step size alpha and the momentum parameter theta. And the thing is that this algorithm is the same, but it's just a different interpretation in terms of Polyak momentum. Yeah, and then if we have this choice, before we use gamma k mk equals s as a choice to get forward backward splitting, if we now have this choice and then instead set alpha k mk equals s, we get forward backward splitting with Polyak momentum. Then it's just a matter of checking that all conditions hold in order to guarantee convergence. So I think this is a quite neat thing with the framework that we get all this also for free. On top of all the methods that we have, we can add Polyak momentum afterwards, and it also goes through. All right, so to summarize, and sorry for going over a few minutes, we have introduced a nonlinear forward-backward map for monotone inclusions AX plus CX, 0 in AX plus CX. We provided two convergent correction schemes because iterating the map itself does not converge for all problems. We had one projection correction scheme and one momentum correction scheme. And then we showed a trick where we put one maximum monotone operator and everything that is single value but not cocoercive into A, and then we subtract everything again using M to effectively move everything from the inverse operation, the resolvent part, let's say the backward part, to the forward part. So we get quite easy nonlinear resolvent update calculations, and the rest of the algorithm will provide us with convergence results. So with that, I would like to thank you for listening, and thanks for the invitation. And again, sorry for going over a few minutes. But I will stay online if you have questions afterwards. So thank you.
Thank you, Pontus. So it's a really nice talk, giving a nice introduction and give a very general framework. For the audience, do you have any questions? Okay, probably I could start first. Actually, you mentioned that from this nonlinear forward-backward splitting, you can end up with a separating hyperplane, and on one direction, you know that the optimal solution is on one side of the separating hyperplane. Then actually, my question is, was it possible to just combine the historical hyperplane that you generate during the iteration and link to the cutting plate algorithm that commonly used in convex optimization?
Yeah, this would for sure be possible to devise such an algorithm. So in a sense, this algorithm is quite stupid because it makes computations with these cutting planes, and then it just throws away everything in the next iteration. So with the things that we have devised so far, and what actually all of these methods also do. But as you say, there are lots of methods that do these cuts and actually keep them and try to project, instead of projecting onto a half space, they might project onto the intersection of many half spaces or so, to have a better approximation of the solution set. And you can actually keep all of them if you want to get an even better all the time. But at the same time, the projection step becomes more and more costly every time you
yes,
as the number of half spaces grows, of course.
Yes.
But we have not explored if there is a good trade-off in storing a few of them. Maybe 5 projection steps or 5 half spaces would be quite cheap still to project on, or 10 or 15. And maybe you don't want to keep only the last few. Maybe you want to keep someone from before. And it might be possible to devise faster algorithms in that way. But we have not done any numerical examples to evaluate that.
And actually, regarding this issue, it seems that once you change the matrix M, the operator M, the cutting plane will change, right? Even for the same point xk, you use the nonlinear forward-backward splitting with different M, you will have different separating hyperplane. And yeah, was it just possible to use multiple separating hyperplane to find out a general improvement direction? Similar to Anderson acceleration, you do different iterations, and then you can see that there is a momentum in one direction, that the optimal solution is in that direction.
Yeah, so do I understand your question correctly, that you mean that you stay at the same xk?
Yeah, and I use different M to run this forward-backward algorithm in parallel, and then I can generate multiple separating hyperplane regarding different MK, and then probably they are in this kind of angle, and you know that actually you can go further instead of using one projection step. Mm-hmm.
Yeah, we haven't tried that one either in practice, but it's for sure doable. And I don't know if I've seen it all in other algorithms either, to stay at the same point. But
yeah, I believe that
I think it's quite difficult to find.
Cheap.
Yeah, it could be quite difficult to find completely different MKs for that are actually even possible to evaluate. But usually there is a step size in MK, so one option would be to do it for different step sizes, but
yeah, then
it might be that they become too similar, so you actually don't gain very much. Okay, x hat k will be different, and then it's hard to say how different it will be, but the risk is that they become too similar, so you waste more computations than you gain by having more hyperplanes.
Okay.
But yeah, it's a good idea, good comments.
Are there any other questions? Probably it's a new mathematical tool to move audience, and then they might need some time to digest the idea.
Yeah,
fortunately, we record the video, they can rewrite the video again on YouTube.
Yeah, maybe if you watch it a few times again, it might be easier. Yeah, it's I think not many people are aware of this monotone operator framework, but I think it's quite powerful. And if you have interest in analysis, it could be good to at least know a bit about it.